My name is Johan Andrén, and I work in the core Akka team at Lightbend. We're 6 people working, I think we're 6 people. About-ish 6 people working full-time on Akka, covering the whole of core Akka, Akka Streams, the cluster remoting stuff, Akka HTTP, Alpaca. So a lot of things. Just get the mouse pointer out of there. And I co-run the Stockholm Scala user group. I think that's enough about me. So what I'm going to talk about today is, or what I'm going to do is give you guys an overview of what's in Akka Cluster. So if someone is here for a different topic, you feel free to leave. I won't be offended. And I want to kind of give you a smorgasbord where you get to see all the cool stuff on top of Akka Cluster. But I won't really dive very deep into each topic. But first, I will start with a little recap around Akka. So could you use both your hands, the fingers of both your hands, or possibly just one, to grade on a scale from 1 to 10 how much you know about Akka? Okay, 10, 10. That's pretty good. Yeah, I'm not sure any one of you need this talk, actually. We'll see. But then I can do the recap really quickly. And also, Nico, right, did the talk yesterday covering pretty much at least the introductory stuff. So an actor is an abstraction that has a mailbox. You can put stuff in the mailbox. It will be executed at some future time on a thread from a thread pool, basically, processing one message in time. That's what the kind of guarantees that Akka gives you. And upon receiving a message, an actor can either send messages to other actors, or it can change its behavior, or it can change its state. That is basically the 3 things an actor can do. So actors communicate with each other through messages, asynchronously, immutable messages. They are arranged in a hierarchy, so an actor always has a parent who is responsible for its failures, just like in real life. If someone has to pay for the damage, that will be the parent. Okay, distributed systems. Some funny quote by Leslie Lamport, but so I would kind of make a concrete thing around distributed system in this form that it's when you try to solve a problem by using many computers instead of a single computer. So that's a pretty kind of short definition. And that is really hard because networks aren't at all the same thing as doing stuff inside of one computer. Like messages get lost, things break. That guy in the IT department happens. Also, you're limited in throughput and latencies and all stuff like that. Okay, so why do it then if it's so hard? Well, 3 rational points. You need to do something that is bigger, needs more processing power than one machine, or maybe a single huge machine that that crazy supercomputer thing that you have a whole gymnastics hall for. That might not be quite worth the money compared to having many small machines that you can kind of use for the same problem. And you can also then maybe scale in, so you run it on 3 machines when you have no load, and then comes Black Friday and you need 50 machines, right? So have you written something for a single system that is much harder to kind of cope with big spikes in processing needs? It might also be about resilience, that you want to make sure that you will always be able to respond even if things are going really south in your data center or whatever. Might not be actually processing requests. It might just be giving a quick response saying, hey, we're not available now. Because the worst thing is when something takes really long time and then times out on something, and you don't really know what's going on and, as a user, right? You want the reply right away that says, yeah, we can't handle your request right now, come back tomorrow or a few minutes or something. So it turns out that the actor model is a really good fit for doing distribution, since communications over networks is packages, messages. And we very often model network interaction as a request-response thing, but that is like an abstraction that doesn't fit so well, right? Because a network allows both sides to send data without the other side initiating it, basically, except for the connection, of course. But as soon as you have a connection, a server could send you 5 responses, for example, for one request, or you could have no request and just... So there could be interaction in both ways, and the idea of RPC is kind of throwing all that away, while actors it's exactly what they model. And we already have this idea of messages being at most once between actors. There's no inherent guarantee that a message will arrive at its destination. So if you need guarantees, you have to build something on top of your actors that does hacking, for example, or knacking. This also fits very well with networks. And one really cool thing that I hadn't thought about before, but Victor Klang, who is deputy CTO of Lightment, pointed out pretty recently, is that with RPC style, like HTTP requests, if you have many kind of layers that are interacting in some kind of distributed process thing, you will always have to reply back to the intermediate guy who sent the request, right? So a client sends a request to your server sends a request to another system, who sends a request to a third system, and the responses needs to go back in that direction, right? So you're waiting for a response in each place. But if you instead model this with messages, then you can pass the message on to the third guy, third node, who will actually reply directly to the node who made the request. So you can model different kinds of interaction than you can with RPC. So we have a local actor system, actor sends messages, or we could split it in two and it's still messages. The big difference is that we need serialization. So that is the way that it's really not opaque, transparent. You will have to have a way to transform your objects into bytes somehow and back into objects on the other side. While in a local system, there is no serialization because that would just be a waste of your CPU. So there's a big thing with distributed systems, and that is that let's say we have a 2-node system, and someone cuts the wire. It's that guy at the IT department. Now we have basically 2 choices. We could keep accepting requests, writes on both sides, and potentially not be consistent, right? Because if you would do a query, you would do 2 writes here and 2 different writes here, and you would query each node, you would get different responses likely, right? You have some kind of state. So you could either accept that you're inconsistent, but being able to always accept requests. So you will always be available, or for the more part be available. Or you could guarantee that you're always consistent, that you don't base any decisions based on different writes on the sides. So instead you stop taking requests when you have this problem with the network or partition between your nodes. And usually people think like, yeah, partitions, but we have a good data center and all that. But in reality, it happens much more often than you would think. And if you're going for the cloud, then it will definitely happen more often than you think, unless you think it happens a lot. Because that's exactly how much it will happen to you. So it could, on top of just being networking things or the virtual infrastructure, if you have containers running your application, it could also be a GC pause on either side, since we're on the JVM, right? So worst case, you could have a second or two of just freezing the system while it does GC. And from the far side, that is impossible to discern. It's not possible to see the difference between that and actually not having contact, right? So you can't really know if this node is, if it's dead, if it's just not responding, if the network is down. There's like no way to determine that. Okay, so I'm going to talk a bit about all the cluster tools in a second, and this is the scale I'm going to kind of put them on. What the tools allows you to build some things that are available or always consistent. And I think it's pretty much impossible unless you have some very large amounts of money and have a company that it starts with a G and ends with Google, and can build your own kind of network infrastructure thingy, so spanner. It's really hard to achieve both of these, if not impossible. So cluster, what I've talked about up until now was you could have two actor systems talking to each other, right? So Akka Cluster is where you have n nodes who all are together in one cluster, and they can send messages across to any other node in the cluster. So it's like a peer-to-peer networking across a set of actor systems. Joining a cluster can be done to any node in the cluster. So you have a new node, you have the cluster, you can go to any of the nodes and say, I want to join the cluster, and you will become a part of the cluster. There is no election process in Akka. We have a leader node at all times, but it's based on a deterministic sorting of the nodes. So if you compare it to kind of a master system where you have a designated master, in Akka, if the leader dies, is taken out of the cluster, that just means that another node is now the master, the leader. And the purpose of the leader is to have a consistent place to do decisions about joining and leaving the cluster, so we don't get inconsistencies in what the idea of which nodes are in the cluster. So each node has kind of a life cycle, and a few of the transitions in the states in this life cycle is things that only the leader can do. Okay? So if I want to make a cluster, but I don't already have a cluster because I want to make a cluster, what do I do? You make that first node join itself, and that will form the cluster. And we have a mechanism of this that Nico talked about yesterday, and that is the seed nodes. And the seed nodes is it's a bit of what should you say? It's a bit misleading because there's two different things in the seed node list. It's the first node. The first node will see if it can talk to any of the other nodes in the list when you start it. If it doesn't get a reply, it will join itself to form the cluster. The rest of the nodes in the list, they will never start a cluster on their own. They will wait for one of the other nodes to be available, right? So if you start a 5-node cluster and you have a seed node list, one of them will join itself, and then the other node will discover that. So they will ping the other nodes in the list for a while. So what happens if we mess that up? Well, you get a split brain. So you will get many small clusters that all think that they are the whole cluster, right? So if you would have something that lives in the cluster and has a consistent state that it needs to keep, an actor that needs to keep a state that you can make business decisions on, you might end up with one of them in each of these mini clusters who all think they're the cluster. So when a node joins or changes its state, this is gossiped inside of the cluster, and also a node is keeping track of a few other nodes to detect if the connection between them is going down. And if it's down, it will change its local view of things, and then it will gossip that to the other nodes. So every second, each node will pick another node at random and then tell it, this is like my version of the view of the state of the world. And the other node will be like, oh, hey, wait a minute. That's different from my view. I need to merge these. And this merge is, the data structure is a CRDT, so we can merge it consistently. We know that we will end up with the same state always on all nodes, eventually. Okay. Each node can be tagged with a few roles. So you could have a cluster, but you have different kind of purposes of the nodes in it. And then you can use these roles in your own code or with the tools to kind of, I want to do the processing on these nodes, and then I want to run the HTTP API on these nodes that have a specific role. Pretty much the entire user API of the cluster itself is a little bit about the node details, like you can see what is my address in the cluster, what is my view of the state in the cluster, and then you can do some imperative kind of, I want to leave the cluster, I want to join the cluster before I'm in it, I want to down another node and say that it's not available anymore, or myself. And we can also register an actor that will get subscribed to events when cluster changes happen. So to listen to these cluster events, that's how all the cluster tools that we'll just soon look at, how they are implemented. Right? So you start an actor, it subscribes to the event, and it will know every time the cluster topology changes, and then it can react on it. So then you can have the same kind of logic happen on all the nodes, even though they don't really communicate with each other. So this is maybe a bit small text to see, but it's minimal 3-node cluster using our new remoting layer, Artery. It's Aaron UDP based. It's not yet quite stable, but it's really, really fast, and it really eats battery on your laptop when you're on a plane to do a conference. So I can recommend that. So this runs a 3-node cluster in the same JVM. But the different actor systems will still communicate across network or the loopback interface. Even though they share the JVM and the same heap, they don't really interact inside of the JVM, but they send each other messages. On all the slides with sample code, I have a little link in the lower right corner where you can follow to a complete sample that you can fork on GitHub and run locally. Okay. That was a long recap. The cluster tools, turns out that there is quite a few things that people want to do over and over again with a cluster in a distributed system. So we try to provide the most common and useful kind of abstractions for building clustering things. So I think I don't have really a good sorting order for them. We will start with distributed data. So distributed data is a pretty neat thing. CRDTs allow you to accept writes on any node, and then eventually that change will reach all the nodes, and you will be able to merge that into a consistent state. So you know that at some point in the future, all the nodes will come to the same state when you have done writes, just that might not be in a little while. It only works for a limited set of data structures, and they need to have some special kind of properties. So they need to be commutative, associative, and monotonic. But with the monotonicity, we can do some sneaky tricks to work around that. So I'm going to tell you about one of these. These are the built-in structures. You can build your own data structures if you really like CRDTs and have read up on it. But I think sets is like an awesome example because it's so easy to explain. So if you have a set, the same thing can only be in it once, right? How many times, doesn't matter how many times you add the thing, it will still be in the set once. So that means that if you have a set on all nodes and you add the same thing, then that will be in the set once when you kind of merge those sets across nodes. As soon as you start removing things, that won't be possible to kind of reach the same state, right? Because you could have the add and the remove in different orders. But let's say then that you have a set that only grows. That is the G set. It will only accept you adding things to it. You can never remove things. Okay? So then we have this monotonically growing kind of data structure. But we can combine it with another set. So we can have a set that is the added things and a set that is the removed things. And the current state of the actual set will be the first set minus the other set, right? So as soon as you have removed something, it's not in the set anymore, and you can merge those, the removed set on all nodes and reach the same state because it can only be removed once then. So it's a pretty good example, I think. Yeah, a few of them. I'm not going to talk more about the individual ones. How it works is that you run what is called a replicator, specific actor, through an extension on all the nodes. And you can perform updates then on any node. You can query the state, like a request-response thing on a node to get the state for a specific key. So it's a bit like a key-value store, you could say, right? You create a key and you can write to that key and query that key. And you can also subscribe to changes on that key. So you can have an actor on one node getting messages every time that node has merged changes from the cluster into a new state. Looks like this in code. Replicator actor, you create a key that has a specific type for the kind of value you have. You'll have an initial value. You can subscribe to the key, and you can send an update then to the key. I think a pretty cool thing is this one, because normally I will get then a response back as soon as it has written locally, but I can also have a higher consistency. So I can say you need to write on more than one node before you tell me that this value was put in the set. Because the risk with writing it on one node is that if that node goes down, crashes, someone pulls the power plug, pours coffee in it, before this change has been gossiped to other nodes, that change is lost, right? So at the cost of speed, latency, you can say this needs to be sent to at least this many nodes before I get an ACK back that I know that it safely was stored. So on the scale, this is always available because you could split your cluster and keep taking writes on both sides of the partition, no problem. And when it heals, it will then arrive at the same kind of state. Yeah. Next tool, distributed PubSub, is actually kind of two tools in one. So the first part of the tool is that you can subscribe to a topic on any node in the cluster through what is called the PubSub mediator, which is also then a special kind of coordinating actor. And you can then you subscribe, and that which subscribers are on each node is gossiped between the nodes. So eventually consistent kind of data structure here as well. And then when you send a message, you send it through this mediator to the topic, and that message will end up at all the subscribers that are known at that time. The message is only passed once between nodes. So if you have like 15 subscribers on one node, the message will only be sent once to that node and then sent to all those 15 nodes. Okay? The other side of the tool is that you can put an actor in there, and it will then be addressable through its path, so its local path, but across the cluster. So this means you could basically talk about an actor that is somewhere in the cluster and interact with it without knowing where it actually lives from the consuming side. It's pretty neat. Subscription part looks like that. This is in code. You get access to the mediator actor. You subscribe to a topic with a named topic. It isn't much more clever than that. There is no hierarchy of topics or anything like that. It's a flat structure. And then you publish stuff also through the mediator to that topic, and the message will end up on all nodes. This is a bit complicated to put on the scale because so which nodes are subscribed to a topic that is gossiped, so that is eventually consistent. It means that if you have a partition, you can subscribe on both sides. And eventually, when the partition heals, you will have the same view of the subscribers on both sides. But during this partition, there is no messages going in between the two halves of the cluster, right? So that means that the messages that you publish during that time, they will only reach the side, your side, basically. So it's not really about consistency, but sort of. And there's like no guarantees of delivery. There is no buffering or anything like that. If you send a message before a subscriber has been gossiped to your node, and it will see it as there is no subscribers, and that will go to dead letters or up in smoke, basically. So if you want to have some kind of guarantees, you will have to build that on top of it. Okay, cluster singleton. So this is maybe a bit of an anti-pattern, but sometimes you have no other choice. So you have something that needs to exist exactly once in the cluster, because it is, I don't know, it's a counter maybe that gives out IDs that can't have holes in them maybe, I don't know. It also has a special kind of actor that you start, which is called the Singleton manager. And you start that on every node, and you give it the props of an actor that is a singleton, and it will make sure that the singleton is pretty much always running on one of the nodes. And you interact through this another actor called singleton proxy, which will know where this singleton is actually alive, if it is alive. So you kind of hide the fact that it can be on different nodes. Okay, if the oldest node where the node where the actor was running before dies, then it's moved to a different node. Yeah, but one thing that I haven't mentioned is the difference between having a node removed from the cluster and just being unreachable. I kind of touched it, but so if we would be in the situation that this node is unreachable, let's say someone actually pulled the power plug to that node, the only thing we know in the rest of the cluster is that we can't contact it, right? So we need to make a kind of a manual decision or use a split-brain resolver to decide that this node is actually taken out of the cluster, and that we are sure that it's not just a partition in between here and the singleton actor is running and still doing things, because this guarantee that we only have it once would kind of fail then. Code, we create a singleton manager, we give it the props, and we create a proxy to interact with the singleton. Also pretty simple. So this is strongly consistent then, rather than always available, because as I said, if you have this network partition, you cannot start a new instance until it has healed, basically, or you know that the other side is down. Okay, last tool. If you really like the idea of having an actor only live, a specific actor instance only live once, but you have a shitload of actor instances. So let's say you have modeled your 5 million users as actors, for example. And then you would want to have a consistency boundary sort of around your actor, where you can make business decisions for your user based on previous events. You don't want to have that actor alive on every node and then take different decisions. Like, oh, this customer was banned because they were, I don't know, posting ugly pics or something. If that happens on one node, you don't want to have a different node allowing interactions or something like that. So sharding allows you to, sorry, I'll go back. Sharding allows you to, given a unique identifier, interact with an actor without actually knowing where it is in the cluster. So cluster sharding will somehow distribute your actors across the nodes, and you will address them through their ID. And this works like this: that you have a shard region on every node, and in a shard region there can be many shards, and in a shard there can be many entities, which is the actors, the concrete actors then. So in this case, we could say that we have customer IDs, which are the A1, A7, B4, C1. And then we have a singleton who coordinates where the shards are in the cluster. So when we add or remove nodes in the cluster, for example, we want to rebalance these shards so that they are spread out over the current topology or the current set of nodes. And to have a consistent view of that, we need to have this shard coordinator. Okay, so we send a message of some kind with this ID, and the shard region will know how to forward that all the way to the entity. If we down a node and we send a new message, the entity will be started on a different node. There's also something called remember entities, which allows you to. So usually if the node goes away, there is nothing starting the entity automatically. It will be started on demand when there is a message for it. But in some cases, you might want to keep the actors alive. Given that you have once created them, you would want to have them still in memory whenever a request comes in. And you can use this remember entity feature. Yeah, it looks like this in code. You, as a developer, are responsible to provide a function that can take messages and extract the entity ID in the payload. That's the extract entity ID function here. So you're also responsible to define a function that can extract a shard ID. So this is something that allows you to kind of spread your actors out across the cluster. Yeah, and then you start a shard region on each node, like this. And you interact through it with your regular message that you have defined extractors for. So it's a kind of straightforward, at least. So this is also on the strong consistency end of the spectrum, because it is all about having an actor alive in one single place at any given time. We spend a lot of time in the team and also the community on the docs, so read the docs for cluster and all the tools. Some kind of a teaser for what we're doing right now and soon. It's of course Akka typed, and we want to move forward with the current Akka typed APIs and do the cluster and remoting stuff, but typed. And also kind of keep backwards compatibility, so you can, to some extent, mix and match the typed actors with the cluster tools. And we're also currently looking into multi-data center stuff, but I'm not sure how much of that will end up in the open source part and how much will become like commercial, on the commercial side. But that will probably be happening sometime in the coming months. Yeah, thanks for listening. Any questions?
Hi, thanks for the talk. I've got a question about Artery. Could you give some comments about how Artery is different from the previous version of remoting, and yeah, whether you recommend to start using it if you're starting a new app, and would you recommend to upgrade to it if you have an existing app with the previous version? Thank you.
Yeah, so we wrote Artery last end of last summer, I think it was, because there were things we were unhappy with the old remoting. I would say most importantly, throughput. So the old remoting pretty much maxes out around some 40,000 messages per second because of kind of inherent constraints in the design. So with Archer, we have been able to push it towards like somewhere between 700,000 and 1 million messages per second. So there's a big difference there. And some of it comes from the fact that we build it on top of Aeron, which is UDP based. But also there's some stuff around the internal, how we have built it that is different. So we're actually using Akka streams internally to build the remoting part of it. I wouldn't say it's production ready, but I would also not say that it's super production unready. So we have people in the community running it in production for sure. So I would say it depends a bit on the timeline of your project. If you're going to put it into production tomorrow, maybe not jump on it. If you have a longer time frame, it might be worth trying out and see. And I mean, if you don't have the limitations, if you're not limited by the current remoting, maybe you're not that desperate to try it out, I'm not sure. But there's some other stuff also. It has some better error handling properties and things like that. So kind of vague, but I hope I answered most of the question at least. Okay, feel free to come talk to me afterwards if you have some more face-to-face arguments you want to make. Thanks again for listening.